Hello out there, everybody, and welcome to a video on some review that we might need for our mechanics and materials class. Um, I'm going to do an example problem here of a shear and bending moment diagram that sort of resembles one of the homework problems that you have for homework set number 1 in this class. So for those of you that haven't seen shear and bending moment diagrams, especially those with distributed loads, hopefully this is helpful for you. So I'm going to put it over to the writing pad, and this is actually going to come from some of the supplemental lecture notes that I included in the course, which you can find on Canvas. So you should see a practice problem in front of you now on my writing pad. This comes from slide number 13 of the supplemental lecture notes on shear and bending moment diagrams that I uploaded to Canvas. So here we go. Let's just get right into it. For the beam and loading shown, draw shear and bending moment diagrams and determine the local minimum and maximum values of the shear and bending moment. This particular image here is symbolic. So I'm actually going to give some numerical values here just to sort of help us on our way. And so let's let the value L, the length here, be 8 feet. And let's let W, which is the distributed load. Typically distributed loads are given in like force per length. We're going to let W here just be a nice round number of 100 pounds per foot. Okay. So what that means here is we got like a 4-foot gap in this first section of the bar and a 4-foot gap here in the second section of the bar. Okay, so you have a homework problem that has a distributed load in it, so I thought this might be a nice one to showcase, and we'll use some actual numerical values here. So let's get right into it. Okay, when you're looking at this beam has 2 major sections to it that I think are pretty easy to identify. So it's pretty clear that sort of on the left-hand side of the beam, I have a distributed load, and on the right-hand side of the beam, I have nothing. So what I'm going to do is I'm going to break this into 2 sections. I'll call this section on the left here section number 1, and I'll call section number 2 here on the right-hand side, section number 2. And so we'll say the domain for each of these is going to be for section 1. We're going to set ourselves a coordinate system, which sort of starts on the left-hand side and moves to the right, which is a one-dimensional coordinate system, x. And we'll say here this is 0 less than or equal to x, which is less than or equal to 4 feet. Okay, so that would encompass the portion of the bar that has the distributed load on it. Then we also have another section, which I call section 2, which is on the domain of 4 feet less than or equal to x less than or equal to 8 feet. And so to handle our shear and bending moment diagrams, what we're going to do is we're going to create equations for the internal shear and internal bending moment in each of those 2 sections by creating free body diagrams in each of those sections and determining what the equation of the shear and bending moment is in each of those sections. Okay, so hopefully that methodology is clear. So let's go ahead and start then by looking at a cut in section number 1 and a free body diagram in section number 1. So this is section 1. Which is, again, on the domain 0 to 8 feet. So the free body diagram on its own is going to look something a bit like this. Here we are with our cut. And I'm going to draw my distributed load in here over the top of this. And since I'm in section number 1, the distributed load is going to act over the entire free body diagram. So here, remember that this distributed load is something like 100 pounds per foot. And I have to include the other portions of the free body diagram, specifically the internal reactions that come from the cut that I made inside the beam. So I will draw that. Traditionally, shear is pointed down. So here is Vx. I have my normal force, Nx. I'm writing these as functions of x. And then I have my bending moment, which is Mx. And remember that the dimension for this cut, how long this bar is a variable dimension. It's the variable x. So this is meant to represent any cut along the bar that exists between the left-hand side of the bar and some location x. And since we're in section 1, that location happens to be between 0 and 4 feet, that first section of the bar. Right? Now, I have a distributed load, and I have to convert that distributed load into an equivalent force in order to sort of execute my shear and bending moment diagram equations correctly. So I'm going to make a new free body diagram here where I write the equivalent force. I'll say here a new free body diagram with equivalent force, and I'll label that as FEQ, right? It's an equivalent force that exists on the bar. And so that's going to look a little bit different after we transfer the distributed load into an equivalent point load. So we're still going to have our shear, our normal, and our moment. But now our equivalent force, 100 pounds per foot, is going to be coming from our distributed load. And in order to calculate the equivalent load that exists, we need to basically determine what is the area of this rectangle that is sort of displayed by these series of arrows that represent the distributed load. So in order to calculate the equivalent load correctly, we would need to multiply the 100 pounds per foot times the distance, x, that is sort of like the linear dimension here. So in this case, we have an equivalent force, which is 100 times x pounds. So if x is 1 foot, we're going to have 100 pounds of equivalent force. If x is 2 feet, 200 pounds, so on and so on and so on. And then it's going to be located at the centroid of this area here, which happens to just be in the middle of this rectangular shape. Okay, so the equivalent load is going to end up being located right in the center. And so we will draw that in our new free body diagram, which here, this is my equivalent load. I'll label it as FEQ, which here is 100 times x pounds, where x is in feet. This happens to be located at a distance of x on 2 away from my cut. Okay, so this is how we convert distributed loads into equivalent loads by figuring out what is the area under that distributed load. So it's the value of the distributed load multiplied by the length, in this case for a rectangle. It's going to be located at the centroid of that aerial structure. So here in the middle of that rectangular structure. All right. So now we're actually ready to do our static equilibrium. And since we're only interested in the shear in the moment, we only need to do some of the forces y and some of the moments. So here, some of the forces y equals 0 gives me the following. It is negative 100 x pounds. That's my equivalent force. And then I'm going to also have the shear force, which is down. So minus Vx equals 0. So we arrange this for the shear inside the beam at any location x, and we'll have that Bx is negative 100x pounds with x in feet. All right. So this is an equation that describes the shear inside of the bar at any location in that first section of the bar. Remember, this is strictly in the first section of the bar. We can also have our sum of the moments. All right, so summing the moments, we have the moment at the location where we cut. This is kind of what we're solving for. And we have contributions to this moment from this equivalent force. All right, so if I'm summing my moments about the cut, let's say I'm summing about that point that I just drew right there. Okay, so I'm summing about this point right here. I reach my arm out towards that equivalent force, curl my fingers. My thumb will be out of the page at me, so a positive contribution. So I have plus the moment arm to that equivalent force is the value x on 2. So here this is x on 2 multiplied by the value of the equivalent force, which here happens to be 100 times x. Equals 0. So we can rearrange this for mx, the moment at any location x inside the bar. And this is just going to be 50x squared, negative 50x squared. And this is foot-pounds for x in feet. Okay, so these two guys are the equations that govern the internal moment and shear inside of the bar at any location x along the first domain, which is this region X between 0 and 4 feet. All right, so these are just two equations that tell you what the shear and the moment are inside those regions. We just got that from enforcing equilibrium and converting our distributed load to a point load and working through that. Okay, so these are two equations that I have. That's for section number 1. Now let's take a look at section number 2. And reminder, the domain for section number 2 is from 4 feet to 8 feet. And so let's look at a free body diagram of that. Okay. Here we go. Here's our beam. We're going to make a cut. And we're cutting in the region where we do not have the distributed load. So if we go back up to our original picture, we are cutting now in the second region. So some arbitrary location in region number 2 is where we're going to make this cut, since we're on that portion of the domain. So if I do my free body diagram, I'm including the full distributed load here over that first 4 feet. This is 100 pounds per foot, and that is over the full 4 feet of that first domain, okay? So since we're cutting in the second region, that first 4 feet is fully represented. Then where we're cutting our bar, we're again going to have some internal shear, some internal bending moment, and don't forget your normal force, even though, we're not necessarily working with the normal force in this problem. It's good to just include it by habit in this problem. All right, and that's all that we really have in our free body diagram this time. Once I've made my cut and I've put in my distributed load, I need to convert that distributed load into a point load. So now, with an equivalent force, I'm going to make a new free body diagram that transfers that distributed load into a point load, still keeping my shear force Vx, my normal force Nx, and my bending moment Mx. All right. Converting this guy to a point load, again, I take the area of this distributed load. So the area of this particular distributed load is 100 pounds per foot times 4 feet. So that's 400 pounds. And it's going to be located at the center of this rectangular structure. So it's going to be located right in the middle of this rectangular structure. So let's go ahead and put that in here. That's 400 pounds. And this is located at that center of that rectangle, which happens to be 2 feet from the left-hand side. Okay, because I know that that distributed load acts over the first 4 feet of the beam. That means that the point load equivalent has to be acting in the middle of that, which is 2 feet from the left-hand side. Reminder that we're making a cut at an arbitrary location, which is the location X. And so this is the general setup for the dimensions and the loads that we're going to use to sort of do our shear and bending calculations to get those equations. Okay, so here we go, some forces in Y. All right, we have our 400 pounds down. We have our shear force down. So again, what we're solving for. And that's it. So in this portion of the bar, we just have a constant value for the shear. And that happens to just be negative 400 pounds. Okay, so that's for this section of the bar. This is section 2 of the bar. Now let's sum our moments. Again, I'm going to sum my moments about this cut, right? So standing at the cut and summing my moments there. We have this discrete moment that's applied inside of the bar, right? It's this internal moment inside of the bar. What we're solving for, the moment at any location X along the length of the bar. And I have to think about how the other forces are contributing to the moment. Well, the shear and the normal force are running right through the point where I'm standing, so they're not going to have any contribution to the moment. The only thing that could possibly contribute to the moment that we haven't considered already is this 400 pounds. And this 400 pounds acts a distance away from the cut, which actually looks like x minus 2 feet. Okay, so make sure that you're using the moment arm correctly when we're thinking about how to account for this 400. So I'll be clear here that this is x minus 2 feet, right? Since I know that my cut length happened at a distance of x, and the equivalent point load happens 2 feet from the left-hand side of the beam. So let's go ahead and sum our moments then, and think about the contribution of that 400 pounds is going to be something like plus the moment arm x minus 2 feet times 400 pounds. 0. I work my magic, figure out what the equation for my moment is. Here, x times 400 is 400x, minus 2 is 800, so we're going to have, look, something like 800 minus 400x foot-pounds. And this is for x in feet. All right, so there's my equation for the moment in this region. And both of these guys, recall, are strictly for region 2. Which, remember, is the domain 4 feet less than or equal to x less than or equal to 8 feet. Okay. There we go. We've figured out equations for the shear and bending moment in both region 1 and region 2. So we're ready to go ahead and sketch what those equations are going to look like by creating our shear and bending moment diagrams. So let's get after it. Here's our sketches. And typically the way that we make these sketches is by sort of showing what the beam looks like and then drawing both the shear and the bending diagram below the beam. It's just a good way to represent like what's happening with the beam. So I'll make a sketch of our little distributed load here. And remember, the side is fixed on the right-hand side. We never really calculated what the loads and moments are on the fixed end. We don't really care. Just moved our way left to right. Doesn't really matter. And now I'm going to make my diagrams by sort of like drawing down here little phantom boundaries. Of each of these two regions. And remember that this was like region 1 and this is like region 2. Okay. So let's make ourselves an x-axis. And here's going to be our shear, Vx. And then down here, we'll have another x-axis. And this is going to be our moment, mx. And I'm going to extend this down just a little bit more, give myself a little bit more room, because I'm going to need it below this axis. But okay, here we go. Let's look at these equations now. We'll start with the shear, and we'll start with the shear in region number 1. I'll scroll all the way back up to where we calculated what's the equation for the shear in region number 1. Here we are. The shear in region number 1 has the equation negative 100x. So if this is between x equals 0 and x equals 4, then we have sort of like left-hand side and right-hand side boundaries of each of these two regions. So if my equation is negative 100x, that means the value of the shear at x equals 0, which, remember, if we have our coordinate system here, I'll put it in here just so we're all clear. X is starting on the left-hand side of the beam and moving to the right. So the initial value of the shear is 0, and the equation is a linear equation, negative 100x. And so the value of the shear at x equals 4 will be negative 400. And it's a linear equation. Just write that in here. Linear equation. Oh, where did that go? Moving between a value of 0 and negative 400 at that boundary. Great. Let's look at the moment equation in region number 1. The moment equation in region number 1 is negative 50x squared. That means that the value of x equals 0, our moment is going to be 0. At the value of x equals 4, we have negative 50 times 16, which is 4 squared. Negative 50 times 16 is negative 800. Right, so we can use those as our two boundaries. So here we have 0, we're x equals 0. And we have a value of negative 800 where x equals 4. All right. So here we have a quadratic equation, right? This is a second order polynomial since we have negative 50x squared. And if we have a negative sign in front of our polynomial, that means that we have sort of a downward inflection. And so we can sketch that accurately by sort of making a parabola with a bit of a downward inflection. So I'll do my best here, sort of make a parabola with a downward inflection. So that looks pretty good to me. All right. Looks like negative x squared. That's what's going on in region number 1. Region number 2, let's take a look at the equations for the shear and the moment in that region. And now we're on the domain 4 feet to 8 feet. All right. So here we go. The shear in that region, negative 400. It's just a constant value. That's nice, pretty easy to deal with. I'm already at negative 400, so all I have to do is just create a straight line. It's still representing negative 400 pounds. Great. For the bending moment, I have 800 minus 400x. Here we have another linear equation, and I want to think about picking out 2 points in the domain that I could use to sort of sketch the solution here. So for this equation at a value of x equals 4 feet, which is kind of like the left-hand side of my domain, I'd have 800 minus 400 times 4, which is 800 minus 1600, which would be negative 800. Right. And at the value of x equals 8 feet, I could do a similar thing. 800 minus 400 times 8, so plug in x here. I'm going to have 800 minus 400 times 8, which is 800 minus 3200. So that gets me a value of negative 2400. Okay. So I can use those 2 points on my graph to sort of sketch this graph. So coming down here, negative 800, I'm already there at the location x equals 4 feet. And then at x equals 8 feet, which is kind of the right-hand side of the beam here, I have to be at negative 2400, which is, you know, maybe down at this location here. And we have a linear equation, so make this a linear line. And there we go, down to 2400. And that's it, my shear and bending moment diagrams. We would typically fill these in back to the value of shear equals 0 and moment equals 0, but kind of filling in those graphs. And there you go, shear and bending moment diagram. So gives you a flavor, an example of distributed loads, how to deal with them. 1C on your homework uses a distributed load, so hopefully you can make your way through that. Still got questions? I'll be available by email. So chat with you guys soon.